There is going to be some math, but so here are the, I guess, 4 topics that I want to talk about before we start doing dynamics. Preliminary math topics. So the first one is going to be by far the longest one. That's ordinary differential equations. Abbreviated ODEs. And then we'll talk about basically extending some things that you're very used to vectors, which you probably haven't done a lot of, but it's not too different. Derivatives of vectors. And this is sort of foreshadowing, foreboding of something that's going to be coming up later in the class that's sort of a tricky but cool topic. So here we're going to be talking about derivatives of vectors in non-rotating coordinate systems. And that's because later in the class we're going to talk about doing some dynamics calculations in coordinate systems that are rotating. In Physics 1, I think mainly you were just told that Newton's laws apply in inertial coordinate systems, which means the origin isn't accelerating and the axes aren't changing orientation. But we're going to be able to apply some corrections and stuff so that we can do calculations in rotating coordinate systems, which is necessary in cases where you don't have full choice of what your coordinate system is going to be. Like if you're taking a measurement, if you're taking measurements using a camera, and that camera's only choice is to be fixed to a satellite or something, then you got to be able to deal with the fact that that camera is just rotating and there's nothing you can do about it. The coordinate system's rotating. So I think that's a really cool topic. But we're starting out with just the coordinate systems that you're used to. Nothing's rotating. And then product rule for vectors. And chain rule for vectors. OD's one, this is the long one. It's short. Okay, so first of all, what's the difference between an ordinary differential equation and a partial differential equation? ODEs have a single independent variable they can have more than one dependent variable. PDEs have more than one independent variable. And, they also can have one or more than one dependent variable. With any differential equation, your goal is to find a dependent variable or variables as functions of the independent variable or variables. So basically, a differential equation is always a relationship that defines a function, and you're trying to find that function or a set of functions. So for example, dy dt plus 5y is equal to 20t squared. You're trying to find a function y of t, where t is the independent variable, y is the dependent variable. And so this is an ordinary differential equation. The only independent variable is t. On the other hand, dy dt, partial of y with respect to t, plus dy dx is equal to 10. You're trying to find y as a function of t and x. So these are the independent variables. This is the dependent variable. And so this is a partial differential equation. You can always recognize partial differential equations because they have partial derivatives in them, because if you have more than one independent variable, your derivatives are partials. In this class, we'll only be solving ODEs. And then besides that, so that's good news, but besides that, we're only going to be dealing with ODEs that you can solve with one solution method, sort of the simplest solution method. So that's more good news. Only solving ODEs, and they'll be solvable using separation of variables. You would use PDEs in, so after statics, you take this and you take deform. And then if you wanted to keep going in the direction of deform, you would start taking continuum mechanics, and continuum mechanics is all PDEs. Fluid mechanics is all PDEs, so that's another place. Those are the two that I'm familiar with. Oh yeah, right. Yep, it gets crazy. Most of the time, if you have to solve partial differential equations, you're just going to be using software. I mean, even it might even be software that you have to write, but the chances of being able to solve a partial differential equation that comes up through like an actual physical problem are pretty low. Oh, also heat transfer. They'll use partial differential equations in heat transfer, but yeah, most of the time you would solve it using software. ODEs are kind of different. You have a much better chance of being able to solve those by hand. But I've never used Wolfram Alpha for this, but Wolfram Alpha apparently has a differential equation solver, and you can just plug ordinary differential equations into it and it'll solve it for you. Mm-hmm. Yeah. You could use your phone on tests. Sure. Yeah, right. That's that's no guarantee that the other classes will let you do that, but that's fine with me. Yeah. Mm-hmm. Yeah. Okay, so separation of variables. The idea here is that you have a derivative that's equal to two functions multiplied together. So first of all, I haven't even finished writing this ODE yet. But how do you know it's an ODE, first of all? It's a differential equation because it's a derivative. It's an ordinary because it's a total derivative instead of a partial derivative. And what is the dependent variable and what's the independent variable? That's right. Dependent is y, independent is t. We're trying to find the function y of t. And with separation of variables, you can write this differential equation in the form some function of the dependent variable times some function of the independent variable. So this is the dependent This is independent. And if you can do that, then you move all the stuff relating to y to one side, all the stuff related to t to the other side. So in this case, you'd have dy over f of y is equal to g of t dt. And now you can integrate this with respect to y, integrate this with respect to t. And use the given boundary conditions to solve for the constants of integration. Yeah, so sometimes it's initial. It doesn't have to be. It could be somewhere else in the domain of the independent variable. But yes, that's an example. Okay, so let's say that we want to solve the differential equation y dot is equal to y squared t squared where y at time equals 0 is equal to 10. So we're looking for a function y of t. We can rewrite this as dy dt is equal to y squared t squared. And then separate it into y to the negative 2 dy is equal to t squared dt. And then integrate both sides. So you get negative y to the minus 1 is equal to t cubed over 3. You have a constant of integration for both of these, so you might as well just combine it into a single constant. Okay, so we have a relationship between y and t, but it still depends on an unknown constant of integration. So now we're going to use the boundary condition. The boundary condition says when t is equal to 0, y is equal to 10. So negative 10 to the minus 1 is equal to 0 cubed over 3 plus c. I just substituted at the boundary condition what we know about y into y, what we know about t into t. And so we get negative 0.1 is equal to c. And so our final relationship says negative y to the minus 1 is equal to t cubed over 3 minus 0.1. Really, style-wise, it would be nice if we wrote y as a function of t. I don't care about that in this class, but you could manipulate this with the, go through the algebra. So you get y to the minus 1 is equal to negative t cubed over 3 minus 0.1. So I can write that as y to the minus 1 is equal to negative t cubed minus 0.3 all over 3.
You apply the negative. You apply multiply the negative to both terms.
Yes, yes, yes. And then so y is a function of time is the reciprocal of this. So 3 over 0.3 minus t cubed. Any questions about that? Yes. The it's another notation specifically for a time derivative. So that means ddt. So it's sort of just shorthand for that's saying that our independent variable is time, and we're taking a derivative with respect to time. It's like y prime, but prime is for any general independent variable. Dot is specifically time. And I guess it's just in physics and mechanics and stuff, you have dependence on time so often that it's nice to have a specific shorthand for that. I don't remember compared to like Leibniz notation. I don't know. I don't know. Mhm. Mhm. Yeah, I mean, for us, it's useful because it's fast. Okay, let's do an example where we do a second order ordinary differential equation. So let's say we have x double dot is equal to 2t squared. And our boundary conditions are when time is equal to 0, x is equal to 2. And when time is equal to 2, x dot is equal to 4. So the way I'm going to think about this is I'm going to do it in 2 steps, separation of variables with each step. So I'm going to think about x double dot as d dt of x dot, right? X double dot is the time derivative of the time derivative. And this is equal to 2t squared. And so now I'm going to separate it into dx dot is equal to 2t squared dt, and integrate both sides. What do you get if you integrate dx dot? X dot, yep, exactly. So this is x dot. This one's equal to 2t cubed over 3, and we combine those two constants of integration. I'll call that C1. We could wait to the end to use the boundary conditions, or at each step you could check to see if there's any boundary conditions you can use. There aren't always, but in this case there is. We could use this relationship. So I'll use the second boundary condition here. We know that when time is equal to 2, x dot is equal to 4. So we have 4 is equal to 2 times 2 cubed over 3 plus C1. So 4 is equal to 16 thirds plus C1. So that's C1 is equal to negative 4 thirds. And now I'm going to update what we know. So now we know that this function x dot is equal to 2t cubed over 3 minus 4 thirds. And now I'll go to the next step. I'm going to rewrite x dot as dx dt. And that's equal to 2t cubed over 3 minus 4 thirds. Separate. You get dx is equal to 2t cubed over 3 minus 4 thirds dt. Integrate both sides. So x is equal to, integrate this with respect to time, you get 2t to the 4th over 12, so that's t to the 4th over 6, minus 4t over 3. Combine the two constants of integration. I'll call that C2. And now we use the first boundary condition. When time is equal to 0, x is equal to 2. So 2 is equal to 0 minus 0 plus C2. So C2 is equal to 2. And so our final expression for x as a function of time is t to the 4th over 6 minus 4t over 3 plus 2. So how do you know how many boundary conditions you're going to need? How do you know if you have enough boundary conditions? Yep, that's exactly right. One for each degree of the derivative. So let me just clarify that. In this one, we started out with x double dot is equal to all this stuff, so we have the second order derivative. Um, so we needed two boundary conditions, and we had them. That doesn't guarantee you can do the problem. You could have boundary conditions that uh, are redundant and they don't give you enough information. But you know you need to. What if this equation had said x double dot plus 2x dot is equal to this? How many boundary conditions would you need? You still only need two, yeah. Although a problem like that you couldn't solve by separation of variables, so we're not going to do problems like that. Okay, what about systems of ordinary differential equations? Um, we'll only do uncoupled systems of ODEs. And what that means is you have a separate equation for each dependent variable. For each dependent variable. So, for example, we'll do problems like x dot is equal to 5xt, y dot is equal to 2y squared, t squared, because we have one equation with x's in it and no y's, and the other equation with y's in it with no x's. But we're not going to do any that are like x dot is equal to 5yt. That would be a coupled system, and then you need a different approach. But with uncoupled systems, if each individual equation can be solved with separation of variables, then you do it as two separate problems. Two separate separation of variables problems. Okay, so let's do this one. So let's say x dot is equal to 5xt, y dot is equal to 2y squared, t squared. By the way, you could see this as a vector equation. It's like this. And that just means the exact same thing as what I wrote. Where the boundary conditions are x when time is equal to 0 is equal to 1, and y when time is equal to 0 is equal to 5. So I'm just going to do the first one first, finish that one, move on to the second one. So the first one, we have dx dt is equal to 5xt. So x to the minus 1 dx is equal to 5t dt. Integrate both of those, you get natural log of the absolute value of x is equal to 5t squared over 2 plus c1. Our boundary condition has x positive, so we can say natural log of 1 is equal to 0 plus c1. Natural log of 1 is 0. So c1 is equal to 0. And so our relationship is natural log of x is equal to 5t squared over 2. And then if you wanted to express this as a function of time, x is a function of time, raise each side, e to each side, you get e to the ln x is x, and this side is e to the power of 5t squared over 2. And then the second equation says dy dt is equal to 2y squared p squared. So y to the negative 2 dy is equal to 2t squared dt. Integrate, and you get negative y to the negative 1 is equal to 2t cubed over 3 plus c2. The relevant boundary condition for that is when t is equal to 0, y is equal to 5. So negative 1/5 is equal to c2. And so our relationship says negative y to the negative 1 is equal to 2t cubed over 3 minus 1/5. For the right side, you can get a common denominator of 15. So negative y to the negative 1 is equal to 10t cubed minus 3 all over 15. And so y as a function of time is equal to negative 15 over the quantity 10t cubed minus 3. Any questions about those? Okay, so now we're going through this list of mathematical preliminaries. That's all you need to know about differential equations. So now we're going on to derivatives of vectors as long as the coordinate system isn't rotating. So derivatives of vectors in non-rotating coordinate systems. And this is going to be important because mainly, I guess there are probably some other cases, but the velocity vector is equal to the time derivative of the position vector. The acceleration vector is time derivative of the velocity vector. The angular acceleration vector is the time derivative of the angular velocity vector. And so the way you do this is if you have a vector u, it's a function of time. And what that means is each of the components is a function of time. So I'm going to write this as the vector u of t is equal to a scalar function ux of t, scalar function uy of t, scalar function uz of t. Then u dot, the vector u dot, is just equal to the vector with where you take the time derivatives of each one of the components. So this is ux dot, uy dot, uz dot. So for example, if you have the vector 2t, t negative 10, and you want to take the time derivative of that, you just get the vector 2, 1, 0.
Will we be doing that matrix and that putting a line on top with a dot on top of that?
What that line just means that everything in there is time derivative. Yeah, I think that's a good notation. It just makes it, where you see it most often is if you have something like 2x, y, t, and it'll be written like this, just to make it clear that we're not talking about 2x dot yt or 2x y dot t or something like that. It's the total derivative of everything. Okay. Next time we'll do product rule and chain rule for vectors. It's a little, so it changes a little bit from the scalar versions, but it's sort of the same idea. Actually, if you have time, I'll give you an assignment for Friday. I'll put it up on D2L. But if you have time, like, think about how you would expect these things to work, the product rule and the chain rule for vectors. Remember that product rule has to do with multiplying things. And how do you multiply vectors? There's sort of two common ways, two ways that are going to be important for us. Cross product and dot product. So product rule there's a product rule for cross product and a product rule for dot product. But besides that, they work about like you would think they would work. Okay, see you Friday.